Hello everybody, in this lecture we will be solving 1988 IMO problem number 5. Here's a view of this problem. Triangle ABC is right angled at point A. So let me go ahead and draw that triangle, if you will. So let's assume that AB is less than AC. Okay, so we have our triangle ABC. This is A, this is angle A here. It measures 90 degrees. We have also B and C here, and D is the foot of the altitude from point A, so we drop an altitude here. This is 90 degrees as well, and we call this point as D. And the straight line joining the incenters of the triangles ABD and ACD so let me go ahead and draw the incircles first. So the angle bisectors would be probably somewhere here. So I have a nice incircle here, a small one, obviously this one is. Okay, and that's the center of that circle. And then I have a larger one, probably something like that. So I'm just doing a rough sketch. I don't want to try to be very accurate here, and that would be the point I2 maybe, I1 and I2 if you will, I sub 1 and I sub 2, and the question is asking for joining these two centers of these two incircles and then figuring out some area relationship. But before I do that, so I will make a few tricks here. So let me go ahead and do it with a separate color here. I will extend line AD first, and what I will do is I will reflect B across the angle bisector here. So let me go ahead and draw the angle bisector here. If I reflect B across the angle bisector, say it hits somewhere here, and I call this point as E, if you will. So let me go ahead and just delete that D writing here. Yeah, so let me write, so the point D is here and E is just below it. And in a similar way, I will reflect C across the angle bisector as well. So that's the angle bisector here. So I claim it would be reflecting across the angle bisector. If I just revise my picture a little bit here, it will hit this point here, which I call it as F. And obviously you guys can imagine how I got the point P, right? So this was a 90-degree angle here, because we are just reflecting across the angle bisector. In a similar way, I will just reflect the point D across both angle bisectors as well. So from the first one, we probably get that, yeah, it should probably end up somewhere here. Let me call that point as M for now, and let's just reflect across the angle bisector here. So if I do that, so this would be a 90-degree angle here, and let me call this point as N, but it would be across the angle bisector, so sorry for that. So these lines would just meet on this side BC, obviously. But now that should be sufficient to come up with some really good constructions. Now I will go ahead and extend this line here, and I would let the line ME, so something like this, intersect this side here. Now a couple of observations are in order. Because BD is tangent to the incircle here, it's not obvious from my drawing, but ME is also tangent to the incircle as well. Remember how we constructed the points E and M by simply reflecting D and B across the angle bisectors. And finally, let me highlight this point as as P. Notice that P, if this is extended, that should definitely hit the point F as well, due to the reflection congruence, obviously, right? So it's kind of getting confusing, so let me write down all these congruences here. So triangle N, so this point here, which I didn't bother calling anything, but let's call it Q, I guess. So triangle NQC is congruent to triangle DQF, triangle DQF. And in a similar way, we have, if I call this tangency point, which is now almost, so the tangency point between ray AI1 and BD as R, if you will, so that point here is R. Then you have MRB, so you have triangle MRB is congruent to triangle DRE here. Yeah, so that's that should do it. But now we have some really good construction going on here. I claim that the shape AMPN is a square. So I claim, so let me claim that. So the claim, and which is very easy to prove, obviously, AMPN is a square, and it's easy to keep track of the side lengths, if you will. Well, first of all, because M and D are reflection of each other across the angle bisector AI1, we know that AM, so let's write the proof. We know that AM is simply equal to AD. But furthermore, we know that AD is equal to AN by that same thing. AD is equal to AN because the points D and N are simply reflections of each other across the angle bisector AI2. And finally, I would like to observe that this line NF is perpendicular to the line AC. So I claim this is a 90-degree angle. So let me actually, probably I should highlight things around. So far I just proved that AM, this side, is equal to AN, this side. And then I already know this is a 90-degree angle. That's a hypothesis of the problem. And now secondly, I can claim easily that this is 90-degree as well, because this is 90-degree and N is simply the reflection of D across the angle bisector, right? So that gives us a pretty decent construction. And because this angle again is 90 degrees, AMR is also 90 degrees here. So now the result is obvious. So you have three 90-degree angles, so this guy is also 90 degrees. Secondly, AM is perpendicular to AN and they measure the same length, so AM is equal to AN by this identity that we just derived due to symmetry. So let's write that, due to symmetry. As a result, it immediately proves the claim that AMPN is a square. But now notice that the little the incircle centered at I1, the diagonal MN of this square will go through that incenter, and it will also go through the incenter I2 as well, due to the nice symmetry, and the sides touching the sides of the incircle touching the sides of the square, and then the incircle touching the square here and here. As a result, this diagonal contains the points I1 and I2 as well. So now, as a final step, we need to calculate the areas, but we have already made significant observations, namely that some areas are already equivalent, as you remember. So let's just make it like this. So let me highlight to you which areas are equal. So first of all, so this, well, the congruences are here basically. So you have C and Q, and the first guy. So this area, this yellow area, is simply equal to this yellow area here, the whole thing, So that's perfect. So I just can, so these two yellow areas are the same. And then furthermore, so let me change my color, I guess. Let's pick this one and let's just adjust the thickness. Oops. So, and then finally, it's very hard to see it, sorry, apologies for that. So this little green one is equal to this little green one here. So those two areas are also equal to each other. Now it is obvious that the so we can now write the side lengths carefully, and hopefully that should suffice. Now we know that the area S, which is the area of triangle ABC, so S is equal to ABC, that thing is simply equal to the area of ABD. I can split it into two, plus ADC, but ABD is equal to AME due to that congruence that I mentioned earlier, AME, plus, and similarly ADC is the same thing as ANF. But now this is beautiful because we have the following thing. This gives us an area which is larger than the area of the square by this area, by this portion. Do you guys agree? Because the green areas here are equivalent and then the yellow ones are equivalent. So therefore I claim that area of ABC is larger than the area of the square by this shaded area that I just shaded, or this part. So therefore this is greater than or equal to the area of AMPN. Now we are about to finish. Notice that by the construction of the problem, we know that the points K, so the point M is in fact the point K by this definition, right? The straight line joining the incenters of the triangles, blah blah blah, would hit AB and AC at K and L. So this is actually point L here. So therefore the area of triangle AKL is half of the area the area of AMPN. So therefore I can replace AMPN with 2 times the area of KAN. Oh, sorry, I should say KAL. And well, the question clearly describes KAL as T, and as a result we have the desired result, right? So we have just proven that S is greater than or equal to 2t by just moving regions around using symmetry, heavily using symmetry, and pretty much not using anything else, no trigonometry or no pi tag, nothing involved. So this is a rather nice result. This is not the only way to prove this problem, obviously. So I already mentioned that you can probably use some trigonometric identities to prove this, or you can even use coordinates like I did in one of my previous lectures, IMO problems, I believe, problem 1987 IMO problem. But anyhow, this one was quite appealing to me, so I wanted to present this solution to you. Hope you enjoyed it and hope to see you guys in our next video.